Machine learning applied to defeat a 30-year-old computer game. Unfortunately, the game was only published in German. However, it's possible to patch the binary file to change the text from German to English directly. This is a game after changing more or less most of the text to English. So you start with selecting how many weeks you want to play, and then the idea of the game is that you have 7 different items, 3 different ice cream flavors, Coca-Cola, cigarettes, well, it's a game from the 1990s, and then bratwurst and french fries. And you buy them from a wholesaler, and then you set the sell prices, and finally you sell everything to the customers. So in fact you have a kind of food truck and sell all these items. The problem that you're facing is to find the optimal sale prices for each of the items given the day of the week, more or less binary if it's a weekday or weekend, and then the temperature. For example, at a high temperature, ice cream will be sold more than a cold day. You start with $10 at the beginning, and then you can try to make most of this money in the time range that you've selected at the beginning. Since we want to apply machine learning methods, we need a large dataset. However, it's tedious to record this dataset by hand. So at this point, what you need is the game mechanics to generate a large dataset of samples and also to allow a reinforcement learning agent to interact with the mechanics directly. The straightforward way to get the game mechanics is to write the author of the original game and ask him for the source code. So you get a nice reply from the author, but the author didn't want to share the source code itself. But this game has a history, and this history reaches back to the 1980s, and for the games of the 1980s, there was source code published in a computer magazine. So I reached out to the authors of the preceding game versions, and the author of the second version was so kind to send me scans of the source code of the 1983 and 1984 version of this game. Based on the source code from the 1984 version of the game, it is possible to deduct the game mechanics of the 1991 version of the game directly. For this you need only a few samples that you can create by hand and then analyze the data and fit the functions parameters of the original mechanics to the 1991 game. You end up with a Python implementation of the game mechanics of the 1983, 84 and 1991 version of the game. Now we have the basis for the machine learning methods. We can generate samples and the reinforcement learning agent can interact with the game. So the task is to find optimal sales prices V for all our items that we are selling in the food truck. And these sales prices are optimal in a way that they optimize the profit P at the end of the day. And they have to optimize the profit P given the temperature TE and the day, which is either weekday or weekend. So you can formalize this as the argmax of V of the function P. In general, there are 3 different machine learning paradigms: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, you learn a model from labeled training data. Then you can use your machine learning model to extrapolate or generalize, to test data, or to use your model to find optimal strategies. The second paradigm, unsupervised learning, will not be used here because we are not dealing with unlabeled data. But the third one, the third column, reinforcement learning, will be used. And in reinforcement learning, you try to maximize a reward signal, in our case the profit at the end of the day. And then you do this by learning from your experience, meaning you use your previous sales history to learn optimal strategies. And in reinforcement learning in general, you have a trade-off between exploration, meaning you try to vary the sales prices to find out if there's a better strategy, and exploitation, meaning that you use the sale prices that you've already find quite good to make a good profit at the end of the day. So these are the machine learning approaches chosen. First, using supervised learning. Here you train a machine learning model of your profit and then use an optimizer to find sales prices V that optimize the profit P given the temperature and the day of the week. So in the first step, you provide input and output, meaning you provide your parameters T, TE and values for your V, for your sales prices, and you use the output of the game, which is a profit given temperature, day of the week and sales prices, and the combination of these two is what we call a training sample. So you provide several hundreds or a million training samples to a machine learning algorithm, which then generates a model for you, which is P star, which is an approximation or expected profit P star, approximation of the function profit. And then in the second step, B, you find the best sales prices V, which maximize the expected profit P star given your temperature and day of the week. The second type or class of approaches is employing reinforcement learning. So you can think of this problem as a k-armed bandit problem. So multi-armed bandits, that's exactly what I said. The problem that we are facing is non-associative. So one situation or state is repeatedly presented with some variations in temperature and day of the week, but we can assume they are independent. And then we evaluate the feedback at the end of the day. In a k-armed bandit problem, you have k different options. Well, here it's formalized as discrete options, but we have 7 different items and we select different or assign different sales prices to each of the items. And we are facing the choice of 7 different values of the actions. So in our case, we have continuous values. And then each choice of action values result in a reward, which is important that the stationary probability distribution, that we do not change the game, that the game mechanic for each day is the same and will not change over time course of playing the game. And the objective, of course, is to maximize the expected total reward over some time or our profit at the end. And we can break it down to optimize the profit after each day of the game. This is a simple incremental implementation. What you can see here is a loop over some steps where the actions that we select are given by this policy here, which is the epsilon greedy policy, where with probability epsilon there's an action randomly selected, or with a probability 1 minus epsilon we take the best action, or in our case the best action values that we have found so far. And then the reward is given by our profit by the game, and then you can either count the number of steps that you have tried, or you can also substitute this here by a constant alpha. That's a constant alpha Monte Carlo method that we're going to use. Then the third approach, we can use deep reinforcement learning, and we can use a state-of-the-art algorithm, in this case a soft actor critic or SAC, and we can ignore the non-associativity of the problem. We can also, of course, set some hyperparameter that makes the non-associativity of the problem less important. And of course, also the reinforcement learning agent will find out that the action that he select will not change the expected reward he will get in the next step because it's independent. The nice thing about using a state-of-the-art algorithm, we can use OpenAI Gym, and then we can use, for example, stable baselines to solve it directly. Fortunately, we know the ground truth of our problem, or as I call it, the optimal Bratwurst strategy. That is, for every temperature, and temperature was TE, and for T, which is either weekend or weekday, and for every sales price, we can extract from the game mechanics what profit we are expecting, and this is color coded in this plot. For example, at a temperature of 0 degrees Celsius, we can go here to this white line, and the white line denotes the optimal values. This is cent. So, and roughly for 400 let's say 49 cents. That would be the optimal sales price for bratwurst at a temperature of 0 degrees on weekend. So we know the ground truth, and now the question is how good our different machine learning approaches approximate the optimal solution or the ground truth solution. First, we look at the machine learning model that we trained with a gradient boosted decision tree, and in total 1 million random samples were used, and then we just use a grid search to find the optimal V maximizing the profit. And what you can see here is again temperature, and then on a weekday. In black you see the optimal value of the sales price for bratwurst, and then in red for bratwurst and a little darker red for French fries. The values extracted from the machine learning model that we trained with the gradient boosted decision tree. What you can see, they roughly approximate the ground truth. The problem that we are facing with this approach is that we are sampling in a high dimensional space. There are 7 different goods, and then there's temperature and the day of the week. And if we want to sample the whole space, we need a lot of samples due to the curse of dimensionality. However, we can reduce the space that we want to sample because we know that our optimal solution will live in a low dimensional hyperplane in this high dimensional space. So what we will use is reinforcement learning, where we sample more specifically in this high dimensional space. Let's employ our Monte Carlo method. So here is a constant alpha Monte Carlo method with alpha 0.2 and the epsilon greedy policy with epsilon 0.5. We use tabular solution method. For this we quantize the possible values of our sales prices into 5-cent intervals, and we only keep 200 best estimates of Q of our action value function in memory. In total, 40,000 runs per temperature and weekend or weekday were performed. And what you can see also here in this result is that because we treat each of this temperature independently, you don't see a good function approximation. It cannot learn that there's a function approximation between the different temperature. However, at each temperature, the predicted the found optimal value of the sales price is quite close to the ground truth. So the question is, with a state-of-the-art deep reinforcement learning algorithm, can we be better in a way that it can learn that there's a function dependence between the different temperature states? And indeed you can. So if you're using the soft actor critic deep reinforcement learning approach, you can see that there's a function approximation of the optimal or the ground truth solution, even though it cannot reproduce this stepwise, the step-like behavior of the ground truth solution. So you see that there's more or less a linear fit to this stepwise function, even though there's a small kink here.